So in this case, we are going to consider our typical part, which is of the AC machines. The first part of our AC machines, which is important actually for us to know the basics of our synchronous machines. We had a part explained from our N5. So here we are just having a continuation, guys. So what we're going to do is to go through. I just need you to go through. We had these formulas. Remember when we're working with this simplified formula. So we're gonna actually this formula, guys. I didn't even know that I was working with this formula. I don't even. All right, it's not a problem. So this is what we talk about in our N5 and so forth. But these formulas that we see, guys, they need like adjustments here. There's these textbooks that we'll be using, guys, But what we need here, I'm gonna put this formula because I was working also with the formula sheet, remember? I explained to you this part of the EMF equation of an alternator. So that is what we had in our N5, guys. And this formula, I'm going to explain much because I explained in N5, we were working with what we had from the formula sheet, guys. And as we have our textbooks, we'll see adjustments that are being made in the textbooks. Not to say there's something that has changed, It is simply one and the same thing. So on the synchronous machines, we are going to be focusing on the EMF equation. That's another part that you need to actually work with, all right? Working with the EMF equation of synchronous alternators, all right? That is of synchronous alternators. As we had in N5 and parallel operation, also that part, the parallel operation of alternators, parallel operation of alternators. You also need to work with the voltage regulation of alternators. So it's a lot, guys, voltage, but it's not that much. All right, it's just that you need to know the basics. So we've got the voltage regulation of alternators. We also consider the synchronous motors. So that is actually the basic view of everything that you're going to need. So guys, I want you to go back to N5, revise everything that you had. We are going to make adjustments like on the formulas because there we use the formula that we were basically focusing with to say the formula sheet because guys, you need the formula sheet, but guys, now we are at a stage that we are supposed to know the formulas that can be adjusted. Know your textbook also because the formula sheet is going to take time in terms of adjustments. We do not know even if there going to be any adjustment. So meaning to say, you as an individual, you need to know the basic formulas and also what you're given in the formula sheet just as an assistance. You're going to use that as an assistance, all right? So in N5, we do not have time. We're just rushing, guys. There was a lot of things. Even now, there's still a lot of things, but we'll see. So you go through this part. Never take this part for granted. Never take this part. Never take this part. Never take this part for granted because they can ask any part. This is the first part that we have. Then we are going to work with the second part again. So this is basically your question number 4. All right. So this is basically your question number 4. This is basically your question 4. So the question 5 will be the part 2 of the AC machines. All right. So they were focusing with what? The synchronous machines. So what exactly are we understanding from the synchronous machines? Synchronous machines. Remember, these are machines which are driven mechanically by prime. These ones. They are driven mechanically by what? By prime. So, guys, we're not gonna be much into there, but I just want you to know that there are two types of AC machines: the synchronous and the asynchronous. So, as we are focusing with what the synchronous machines, which is going to affect us in the calculation of the EMF equation of the synchronous alternators, which are the AC generators. So you're actually working with what? AC generators. So that is the first part of our topic, the subtopic that you're going to work with. So for the basic view, guys, so that we do not waste much time, just go through your basics of your N5. You'll see that it won't give us that much problem. All right. So like I said, I'm just going to have this as my subtopic A, which is working with the EMF equation. So that is the EMF equation of a synchronous. Then on this part, guys, of a synchronous alternator, on this part, guys, it is important that you do understand that formulas can be adjusted to suit the question. So you might have your textbook, depending with the source that you're having being adjusted. Use the way that you understand. It is still one and the same thing. So we saw that from our previous case in our N5, we actually supposed to have our formula as the EMF equation, which is the induced EMF per phase. So we're going to use the P to denote per phase, this part. We're going to use it per what? Per phase. They can use any part depending with your textbook. All right. So this is the formula that we're going to work with, guys, which is 4F, then the flux, useful flux, times the turns per phase. We're going to have the constant, which is the form factor. Then also we've got the pitch factor, which is a constant, the distribution factor. So this is what you are going to need when you're calculating what? The induced EMF per phase. If we check your formula sheet, you'll see the formula written as 2KF, KD, KP like this, frequency, useful flux. Then we've got Z, which is the number of what? The number of conductors. This formula, guys, we're still talking about one and the same thing. So it will depend with what you're going to have. So just because of the new adjustment, as for me, I'm focusing much with the TVET series collection. Guys, I'm not saying focus with that one. Focus with whatever part that you're having, but we can also have those formulas. We are going to add questions from different textbooks, but adjusting or using the formula that we are going to be having. In this case, I think for the basic that we all have, we're just going to use this one. All right. So I'm going to explain what we have on our formula. So we are saying we are calculating what? The induced EMF per phase, which is our EP, induced EMF. That is the EMF equation. So that is our induced EMF per phase. Take note, we are dealing with what? You are dealing with what? Connections which are in star, in delta, three phase. So you'll be given the line voltage, which is what? Can be used to give us the phase voltage, which is our induced EMF per phase. It's a phase value, this one. It is what? A phase value. So meaning to say, when you are given conditions from a question, the EMF that you be given at an open circuit is your line voltage. This is what? At open circuit. So that will be representing your line voltage. This is the line. Then we need what? The phase value. So that value will be like, unless they give you any other way, but you take it as your line value. Then you have to calculate what? The phase value from there. So this is the idea. So we have got, like I said, guys, here, just for you to know this part, we said EP is what? That's our induced EMF per phase. So we've got our induced EMF per phase. Then we have our F, which is representing the frequency. So definitely, guys, you know your voltage measured in what? In volts. Then we have got our frequency. As we know, our frequency is measured in what? Is measured in hertz. Then we also have the useful flux per pole. That is the useful flux, which we are given per pole. The useful flux per what? Per pole in what? In Webers. So remember the units, it is measured in Webers. Then we've got TP. Once you see the P there, phase, these are phase values. So TP will represent the number of turns per what? Per pole. That is per phase. I mean, we are representing the number of turns per phase. Per phase. Number, all right. That's the number of turns per what? Per phase. Then we also have KF, which is a constant. So this is a constant from our form factor. So that's our form factor. Remember, guys, your form factor, even from your industrial electronics end form, it's just a ratio that we have of the RMS value to the what? To the average value. RMS to the what? To the average value, which you can write like this, average value. And we saw that it will give us 1,11 from our calculations. So in case of the form factor, you are going to use that as what? 1,11 unless stated otherwise. All right? Unless stated otherwise. Unless you are given something. Unless you're given a certain value, that is what you have to consider. But in your normal presentation, you must use what? 1,11 from what? RMS value that we have to the average value. We also have KP here, which is the pitch, P for the pitch. So that is the pitch factor. So all these, they will make sense if we explain them. Then KD is the distribution. Let's just write our formula, guys. That is our distribution factor. All right. So we've got the distribution factor. So like I said, all these will make sense if we go through each in explanation so that we'll see. So this formula, guys, is going to help us in calculations, not just of the induced EMF. No, anything. You might need the useful flux from the per pole. You might need the number of turns per phase. You might need anything which is to be used on those calculations that we are going to list. Any other calculation that you might be given. So like I said, others might use the formula, which is 2KF KD KP times the frequency, useful flux, and the number of conductors you can You have this formula as it is from your formula sheet. So guys, do not say this formula is wrong. It's still one and the same. And to note what exactly are you working with, because as long you are working with what? Line values and the phase values, you must remember the connections that you are given. So remember your connections, guys, in a star connection, working with a star connection, or we are working with what? With a delta connection. No, your connections that in a star, the line voltage, so in this case, we're going to talk of what? EL is equal to what? Square root of 3 of the phase value. So in this case, as we are to see on our calculation, we are dealing with what? The phase value. So therefore, the phase terminal voltage that we have is going to be what? The line voltage, which is the line value that we have over the square root of 3. We just have to divide by what? The square root of 3. Where in delta, they are exactly the same in terms of the EMF. We are focusing on the EMF. So this is another part that you need to know, the connection that you're working with. All right, so there I'm not going to waste much time. Let us quickly go through some of the terms which are on the formulas, on the formula that we are given, and also what you are supposed to expect in terms of the calculations, what you might be given. So like I said, all given generated EMFs, open circuit voltages are line values unless stated otherwise. You're supposed to know that, guys. All given. As long as a generated EMF, you take it what? As a line, then you calculate the phase value from there. All right. Then also going through your N5, you are going to be focusing with the formulas. We talked about what? KF, our form factor. So let's talk about the form factor. Then guys know those type of degrees. Remember type of degrees. You've got electrical degrees, mechanical degrees. Go through that part, the theory. It will be important, your N5 theory as it was. So let's just consider these factors as we have considered the form factor already. We have talked about this, guys, RMS value to the what? Average value. So I'm going to talk about the pitch factor. All right, pitch factor, which is important also in your calculations. As we can see, it is part of the formula. So without that pitch factor, it means that formula is affected. So the pitch factor, what exactly are we talking about? This is the ratio of the actual EMF obtained to the EMF that would be obtained if all coils were full pitched. So if we talk about the pitching, guys, all right, let me write this one. I thought that I'm not going to write it. So I'm saying is the ratio. So this one is going to be the ratio of the actual. So we are considering the actual EMF obtained, something that you have what? Obtained, to the EMF that would, meaning to say it is not being, that is what we are expecting to have, that would be obtained. All right. In which condition, if all the coils, were what? Full pitched. Were full pitched, I mean, sorry for that, were full pitched. Remember, in your N5, when you talk about the coils being full pitched, it means in that consideration, our pitch factor will be equal to 1. So that is the condition that would be obtained. But in a normal consideration, we are not going to be given that. It is going to depend with the pitch factor value that we are given. The part of what? The pitch. So this one, guys, we need to actually understand our part of what? The pitch factor. Fully pitched, our KP was supposed to be what? To be 1. So meaning to say, it can not be, it can be affected when it is not fully pitched. This is a condition where you have the short pitched coils. So the short pitched coils which are not full pitched, take note, they have conditions which follow them now. They have what? Conditions which follow them. So we are going to see that in our calculations, so that, guys, because if I try to put this into like detail, one of it, it's going to affect us. So let us just go to the formulas straightforward. Then as we'll be explaining examples, we'll be adding this information. So our pitch factor can be calculated, guys. We can determine this, which is also given in our formula sheet. All right. So calculating the pitch factor, it is the cos of, so we're going to need the angle of the short chord. The angle of what? The short chord. So this is the angle of the short chord over what? Over 2. The angle of the short chord. So this is just a Greek letter, guys, which is psi. I don't know how you pronounce it, but that is a Greek letter that we just consider there. So it represents the angle of what? Of short chord. The angle of what? Short chord. So that is the part that we are going to need there, the angle of short chord. So with that, we can calculate our pitch factor. So guys, depending with the situation here of the angle of short chord, it's going to depend with the condition. Let's talk about this, the angle of the short chord. All right, so you can just allow me, guys, to remove this part, because I just wanted you to, that's like a recall to say, where are we coming from? But I can just remove this. I want to explain something from this part. Okay, sorry for that. I wasn't supposed to do this, but let me just do it here. I wanted you to see this. This part is going to affect you in determining the angle of the short chord. So in a full pitched consideration, it means we do not have any short chord. The short, guys, the piece that is remaining when there is a span. So in our normal consideration, let's say like this condition 2, we can understand from condition 2. We are saying we have got a full part here, which is the pole pitch of 180 electrical degrees. All right, which is the whole of this line that we are seeing here. It's 180 degrees. We are saying the whole angle, you take it as what? 180 degrees. So let's say our coil span is 130 degrees. This is our span. All right, this part here, representing your span. The remaining part out of the 180 degrees, the remaining part is our short chord, this part here. The remaining part, what is remaining is the angle of what? Shortcut, this one. The angle of shortcut. What is remaining? So this part that is remaining, since we're talking about 180 degrees, guys, maybe we have got a span of 150, we've got a span of 130 degrees. Out of 180, we're going to subtract that angle that you're given. So meaning to say, our angle of shortcut is going to be 180 minus the angle that is of the span that you're given. So it depends with what you are given. What are you given? The condition. Let's say they are saying you're given a fraction, like for this one, 3/4 coil span, 3/4 of what? Pole pitch. 3/4 of pole pitch. This is our pole pitch, 180 degrees. So it means our span in this case is what? 3/4 of what? The pole pitch. Our pole pitch, guys, is what? Always at 180 degrees. 180 electrical degrees. Always. So means say if it is 3/4 of that, they can say 1/5, 4/5, whatever that you're given there. You find the angle that you're given, all right? So let's say, for example, this one that we have, 3/4 times what? 180. This is the 3/4. You get 135 degrees. So what does it mean? The 135 degrees is the 3/4 that we are seeing here. It is the 135 degrees. So what about what is remaining? If the span we are taking 135, it is just like what we had here, 130. So what is remaining, this one? It will be 180 electrical. Remember, these are what? Electrical degrees. Minus what? 135, the angle that you're given. You get what? 45 electrical degrees. From this understanding. But also from the understanding of, to say, you covered a certain fraction. If it is 3/4, it means you have covered the 3/4. This is the part of what? The span. Out of the 3/4, what is remaining? It will be 1 minus what? 3/4, which is what? 1/4. The 1/4 that is remaining is our angle of what? Shortcut. Meaning to say the angle of shortcut will be the fraction that is remaining, the remaining part. We always talk about the shortcut, the remaining part out of the span. So the span need to be every condition. There will be different conditions for that span. What are you given? You work with that condition. So like I said, guys, we're not gonna talk much about that because we just need a condition there. What are they saying? You work with what are they saying? All right. So that is all about the angle of the shortcut. So from there, you can calculate your what? Your pitch factor. All right. Another part, the form factor, guys, we talked about this. Then the distribution factor. Let's move on to the distribution factor, which is another part which is important. So they can also ask you to, you might be asked to calculate what? The distribution factor. All right. Another part. Okay. No, I'll edit on the question. No problem. I'll edit when you're dealing with questions. Distribution factor. So the distribution factor, that's our KD, can be written in short as what? As KD. All right. Let me add this part, guys, before I forget, because I might say I'll add this part when we are doing questions. Then when we are doing those questions, we'll end up even forgetting that part again and again and again. So our pitch factor, remember they were talking about the issue of the span, this and that. So they can call it the coil span factor. The pitch factor can be referred as the coil span factor. So when you are being asked to calculate the coil span factor, they're asking you to calculate what? The pitch factor. That's another name they can use there. All right. So I'm not going to add much. All right. No problem. So like I said, we also have the distribution factor. So this is also a ratio of the actual EMF obtained to the EMF that would be obtained if all the conductors this time were concentrated in one slot only. All right, what are we trying to say here? Is the what? Is the ratio. So this is the ratio of the actual EMF obtained. So that is the actual EMF obtained to the EMF that we are supposed to, that we're expecting to have that would be obtained. In which condition, if all, take note, if all the conductors this time, if all the conductors were concentrated in one slot only, were concentrated in what? In one slot only. They can ask you these definitions, guys. Know these definitions. So we are simply referring to, say, remember from the stator conditions, we can have the slots with the number of conductors. But we are saying if they could be concentrated in one slot, all conductors. Remember, in a normal consideration, you're supposed to be having something like this. Let's say, guys, in terms of drawing, me, I'm not good in these drawings things, but I just hope you understand. So let's say we have got a consideration of a stator with 4 slots. All right, can we just have 4 slots here? That's another part here. All right, like I said, guys, me in terms of these drawings, I'm not good. So let's say we've got a condition of a stator with 4 slots with 6 conductors per slot. So we'll be having conductors 1, 2, 3, 4, 5, 6. 6 conductors per what? Per slot. But in our case, we are considering a condition that could have happened, or if all the conductors were being concentrated in one slot. Only one slot. Remember, this is the slot that we're talking about here. We're talking about a slot with what? 6 conductors. With 6 conductors. So if we can take in one, so that is the definition that we are having there. So in actual sense, you'll be given or you'll be asked to calculate this, your distribution factor. So your distribution factor KD can be calculated from this formula. Let me just write a little bit here on top. So our KD is also, we've got this in our formula sheet, the sine N. So I'm going to use this one, the gamma, this one over what? Over 2. All right, over what? That's N sine of what? Gamma over 2, like this. So thus, from our formula sheet, the gamma that we are seeing, they can give you this as alpha, angle alpha. This is what you have from your formula sheet. They use what? Alpha, like this. It's just one and the same. So your textbook might be using alpha. Maintain that alpha. Your textbook might be using gamma. Maintain the letter gamma. They can use any letter. Maintain the letter that you're given. So in this case, N, this N here, is representing the number of slots per pole per phase. That is our number of what? Slots per pole per phase. Per phase. So guys, here you can write per phase. Remember per. We talked about this pair in our N5. Once you see that pair, multiply by what is after pair to remove that pair, to get rid of pair. To put pair, to have pair, you must divide number of slots over. The moment I say number of slots, total like this, the moment I say total number of slots over, let's say pole like this, I say total number of what? Of poles. The moment I use something like this, number of this over number of, it means slots per. Whatever answer that I'm going to get here, it will be slots per what? Pole. Slots per pole. So to remove that, we must multiply with what follows. To get rid of this pair, you multiply by the number of poles. Meaning to say you'll be just having this. So it depends with what you're given. What is it pole per phase? Guys, it can be from here. They can give you information of these two. So pole per phase, what does it mean? It means you had the total number of what? Of poles over what? Number of phase. This is the part which gave us what? Pole per phase, this one. From our understanding of pair. All right? So we're going to use any for now. Don't take any part like to mean any other part. All right. They can use any presentation, guys, depending on your textbook. Again, as for me, I'm just going to use letter N so that we do not have confusion. Then our gamma, in that case, what does it represent? Definitely, we are talking of what? An angle. Yes, sign of this. This is supposed to be what? An angle. But which angle is it that you're talking about? That is our slot pitch or the size of the slot. So this is our slot pitch or size of what? Size of the slot. So on this one, guys, we must be careful on this gamma, this one, all right? This gamma. It's just gamma like this. You can use Y as it is, or you can just use gamma, guys. Understand any part. Like I said, in your formula sheet, they used alpha. They can use alpha. Depend. So textbooks, now if you check your formula sheets, they follow not the, if you check, the memo, they follow not the formula sheet now. Now they follow the textbook to say this time we are using information from this textbook. So they just like use those formulas. Not to say your formulas, they are wrong. Maintain your formulas, guys. What you know, maintain to that. Don't bother another calculation to say they worked it like this, so I'm wrong. No. Check the answers at the end. Are they correct? All right. Check the answers at the end. So we are saying the gamma there is the slot pitch or the size of what? Size of slot. So it is important that we understand the slot pitch. Slot pitch. Where is it being taken from? Remember when we had this idea, let's just hope it's gonna mean something. Remember when we had this presentation of the diagram presentation, we say the whole of this part here is representing our pole pitch, right? Remember, this is your pole pitch, which is 180 degrees, electrical degrees. The span is going to take a part, which is your what? Your span. Then there's a piece which remains, which is this one that we have been focusing with before. That was remaining. The piece that is remaining, this one. And we are saying it is the short chord, angle of short chord. Okay. they can give us a condition, guys, whereby you are working with let's just say they are limiting the information for us to consider the slot pitch. They limit information for us to consider the slot pitch like this. I want us to understand about this slot pitch with what is remaining. All right. Remember, we have a part which is remaining, which is our shortcode. All right. So let's put this, our shortcode. Angle of what? Of shortcode. So you understand me very soon here. So this is it. This part which is remaining, they will give us a statement like the 410 coils are short coded by 2 slots. You want to get this part. Let's say they gave us a condition like that. We've got a 410, like whatever that we have, but being what? Short coded. Then they will give you now the condition of that by. Then they can say maybe 2 slots. 1 slot. What does it mean? So this is the idea. Here at the end where we have the angle of shortcode. Remember, this is the angle of shortcode which is remaining. But they're saying it is what? Short-coded by 2 slots. Meaning to say it will be subdivided. This angle of shortcode will be divided into 2. It is no longer, it will be now divided into 2 like this. Where we've got the first part here and the second part representing what? Our slot pitch or the size of the slot. Remember, they are saying 2 slots. So this is the first one and the second one. So we need to find this now, which is what? Our slot pitch, in order for us to have the angle of shortcut. In this condition, when it is of 2 slots like this, therefore it will mean what? It will mean that our angle of shortcut is equal to 2 times these ones. So it's going to be 2 times what? The slot pitch, our gamma, 2 times. This is the condition what they gave us to say is 2 slots, short-coded by 2 slots. They can say it's short-coded by what? 1 slot. When it is that way, it means the whole of this part that is remaining, it is equivalent to 1 slot. The part that is remaining, it is equivalent to gamma. So in that case, our angle of shortcut will be equal to what? Our angle of shortcut will be equal to gamma, which is our slot P. They will be equal for a 1 slot. So you need to understand the information. What is about the slots that are remaining to obtain what? Our shortcode from there. So as you can see, the shortcode can be calculated if we have what? The slot pitch, the angle of the slot. If this one is there. But as you can see, we might not be given. We might not be having this information from here. So how can we calculate now the slot pitch? That is the question. So the slot pitch can be calculated using this formula. All right, so let me write it here. Okay, this part, maybe it's gonna, but I'll explain when you're doing questions. All right, no problem. Let me do it here, guys, because I'll forget. Let me just do it here. So you said we can calculate y in this case, which is, our gamma. So the way that I'm writing now, I'm just taking like y there. It's just our gamma there. You can use alpha, like I said, guys, all right? So to calculate or to find that slot pitch or the size of slot. To calculate, okay, our gamma. So this is our gamma, which is what alpha can be used as alpha from the formula sheet. They can use alpha there. All right. So remember, that's our slot pitch here. So this can be calculated from the electrical degrees of the pole pitch as it is, 180 degrees. Remember the 180 up to the end there. All right. So it follows that our gamma is equal to 180 electrical degrees over slots per pole. Over slots per what? Per pole. So as you can see, guys, we are saying slots per pole. Per. To have that per, it means we had a total of this over total this. Slots per pole. This part of per, this per that. All right, so I'm just going to end with that part of per, the per values. Then we do question papers because, guys, I'll end up like as if I'm now back to the N5 here. Keep on explaining this part. So I want you to, as you're answering these questions, to, I don't know, memorize, but just try to understand this about these pair values. Those pair values. Tens per pole. Tens per phase. What does it mean? Conductors per phase. Per. So once you have per certain value, you are going to divide total. You use total of that. Like, let's just say a simple part. We need per, remember? So let's just say slots per pole. Slots per pole. For us to have the slots per, it's like this: slots over poles. That is what it means. Per. So you have to use the total of what you are given to this one, which is per, you are dividing with. So it's simply total number. I'm just going to write in short, guys, because of time. Total number of what? Of slots. Over what? Pole. The pole there is the total number of poles. Total number of poles. So slots over pole. Slots over pole. It gives us that slots per pole. Whatever that you want to calculate with per, that is how you calculate it. Anything, guys. Any. Think of anything. That here is per. You use that condition. All right. So you can talk of the slots per pole. We can talk of conductors per slot. What does it mean? Conductors per slot. Per slot. It means this over this per. But it must be total. So you must be talking of what? Total conductors. Total number of what? Of conductors. Total number of conductors. It must be from a total. All right? Total number of to this total again. Total slots. That must be the case. It must give us per value of what we need. Remember, number conductors is Z, so we can even talk of what? Z total. Over what? Total slots. This is just for you to add in your revisions. Pair this. We are talking about pair values. Conductors, pair phase. What does it mean? Conductors, pair, phase, pair what? Pair. Total this to total this. So it simply means total what? Total number of conductors. All right. Total number of conductors over what? Number of phase. Total of phase, which is the number of phase. Is it 3 phase? Definitely we're talking about 3 phase in your calculation. So use 3. Number of phase. Hey, that. So guys, I cannot end this because it can be anything. It can be anything, guys. It can be anything. All right? It can be anything. So these formulas that we see here, or the idea of this pair value, is simply to divide with what you're given with the other part that follows pair. But do not mistaken to tens per phase the way that we understand it. The tens per phase, the way that we understand it from our N5 part of tens per phase. We are not supposed to take that aside because of what? Because of these calculations that we have been talking about, the tens, where we've got pair values. This one, it can be calculated TP, tens, per what? Per phase. So the tens per phase, which is referred as TP, can be calculated this from special formula if we have the number of conductors per phase divided by what? By 2. Number of conductors per phase divided by what? By 2. So meaning to say, if I have one of these, I can find another. I can even find number of conductors per phase if I'm given what? The tens per phase. So this one is a direct formula, which we have. All right. Then we saw that we are saying to put pair, to have this pair, we are supposed to divide with what follows after pair. So how do we get rid of pair? How do we get rid of pair? Get rid of pair. How do we get rid of that pair? Let's say we want now the total number of slots. Anything that is to be total of this. So to get rid of pair, you will be calculating what? Total values. You will be calculating total values of what is given before pair. Total values of what is given before pair. Remember, our major part is working with the word pair. So guys, for you not to miss calculations that you're going to have after this, make sure that you become part of the membership because we're going to be having classes working with examples, typical exam questions. Like I said, this part of the EMF equation, there are questions from question papers that you're actually supposed to know before you even move to the parallel, this operation of alternators. Check November, supposed to be November 2013, November 2023. Check November 2024, question number 4. It is all this information that I'm explaining. All this information. Check those papers. Question number 4. So make sure that you follow up all the classes up to the end, which will be definitely be posted on membership so that you do not miss any of the classes. So this is what I'm trying to say. To get rid of pair, you're calculating the total values of what is given before pair. So let's just take one part. I'm just going to put one example here. We said conductors per phase. So meaning to say, when the question is asking you to calculate total conductors, you are being asked to calculate what? Total conductors, or you need total conductors. Whenever you need a total, check for a statement that has a pair for that part. Check for a statement. So if I have a statement like this one, let's say, I'm saying here, let's say we have a statement like what? Conductors per phase. Let's say we are given. Let's say we are given. I'm saying, let's say we are given what? Conductors per phase. This is what you're given. And the question needs you to calculate the total number of conductors. That's where we get, that's where we're talking. That's the part that I'm talking about there. You're calculating the total of this. What is before pair? Conductors, total conductors. So how do we get rid of pair? We multiply with what follows after pair. After pair, this one. To get rid of, you multiply by that, what follows after. So meaning to say, using this consideration, I will simply say the total number of conductors is what? Conductors. Number of what? Conductors. Times. Now I get rid. Remember, pair means over. So to remove over, I have to what? Multiply by what follows after pair. So it's now times what? Number of pairs. That will be the condition now. To get rid, whenever you want to get rid of pair, you must multiply by what follows after pair. All right? So you will be calculating, guys, take note, guys. Yeah, please, here. You will be calculating what? Total values. Every time you get rid of pair, you'll be calculating a total value. So those will be total values. There will be total values of what? What is given before pair. Meaning to say is total number of what? Conductors. Questions will be back now. You'll be reversing here. These ones. You were saying conductors per phase. So you are now reversing. You are now calculating what? Total conductors. All right? You were having conductors per slot. You are now calculating total conduct. Meaning to say if you are given this, you must use what? Conductors times number of slots. You want to calculate the total slots. If there is a statement about the slots per pole, then you must multiply slots times number of poles to remove pair. That is the idea of the pair values. So it is all about what you are given. So these are some of the typical parts that you might be given. I'm not saying stick to this. They can give you any of this. All right. So to remove these pair values, mostly in removing or on the removal of the pair values, those would be questions like we talked about also these questions in our N5, but I want you to add on your notes because you need these. Those will be total values, like I said, like total conductors, all right? So as for total conductors, which is our Z total, it will depend with the information that you are given. Let's say you are given a number of slots per conductors. Number of slots per conductors. Number of conductors per slot. Meaning to say it must be number of conductors per slot times what? Number of slots. If you are given that, number of what? Conductors times what? number of slots. This must be from a condition when you were given conductors per slot. So I'm just writing in short, guys, conductors. It must be from conductors per what? Per slot. If you have this on your information, you use it to find what? Z total. So you might not be given this. You might be given something else. You might be given a condition, maybe it's conductors per what? Per phase. Let's say it was conductors per phase. How do you remove per phase? You multiply by per phase. So Z total can also be calculated from that. We can calculate Z total from what? From that. Per phase value times number of phases. So meaning to say Z total can be given from ZP times what? Number of phases. This must be from what? Number of conductors per phase. If you are given number of conductors per phase, then you can remove it by multiplying by what? Number of phases. So I cannot finish this part, guys, with the conditions. These are some of the conditions that you just need to add as you are studying. They can ask you to calculate the total number of slots. Total number of slots. Maybe you are given the number of slots per pole per phase. Given number of what? Given number of slots per pole per phase. Let's say this is what you're given. Number of slots per pole per. We need to calculate what? Total number of slots, this one, before per. So to have this, we are going to use what? N, which is, so I'm going to use N to represent the number of slots per pole per phase, that one. So we are going to multiply by what? Remember, we need to remove per. Per what? Per pole. So you multiply by what? Total poles. All right? You are supposed to multiply by total poles. There is a pair here. To remove pair, you multiply by what? Total of that. Which is the number of what? Phases. In this case, we cannot say total, but let's just say number of phases. Number of phases. We have removed this number of slots per phase, number of slots per pole per phase. We have removed it with the multiplication. So to know more about how to work out these calculations and typical questions that you might be given, make sure you go through the membership platform. Like I said, we are going to add more questions as we shall be having examples. Our next part shall be working with examples. Try to figure out how to use these formulas, and yeah, that is what you're going to be doing. So let's meet again in another class. Till we meet again, guys.